So, all right, so let's get started. So welcome back, everyone. So today we're going to start a new section on dimensionality reduction. This is going to be the most this part of the course will be most intensive in the linear algebra.
Let's get started.
All right. Okay. What we're going to do, we're going to cover this over 4 lectures. I've often taught the data mining course, and basically when I first started teaching that, I would cover basically this material over what we're going to do in about 4 lectures roughly, and so 1 lecture, and I realized it was too fast. And so we're going to kind of spread this out over 4 lectures and maybe add a few other things beyond what's covered in that class as well. And so we just finished the section on gradient descent. And so I would say this you are in the middle of the most, both probably homework-wise most challenging and conceptually most challenging part of the course. We're introducing a lot of new ideas, combining a lot of things you've learned over the semester together. And so if something didn't quite click now, then it's going to be difficult to synthesize that with something else. So after the dimensionality reduction part, or towards the second half of this, once it becomes more clear, then we're going to be using the same sort of tools again, just for different problems in the rest of the class, right? So this is I know this is where it gets challenging for students, so hang in there. We'll try and go gradually. I think you'll make it out on the other side, understanding stuff so much better. Homework 3 was due on Tuesday. As I mentioned, that one took a little bit longer than probably the first 2 homeworks, especially for some people, especially if Python was unfamiliar. Homework 4, which we will have out by Tuesday next week, is also going to be like that. We're going to be combining together the 2 Python exercises you did in homework 3 in homework 4. So the rest of the homework should be more straightforward, okay? But that task you're going to do, you're going to implement what was described in the lecture on Tuesday. A simple version of that is really the core of what machine learning is doing. You're taking data, you're transforming that data into a function that you want to optimize, and that is where it's optimized over the parameters of a model, and then you're running gradient descent over those choice of parameters to optimize its fit to the data. Okay, what we covered on Tuesday is the simplest version of that, and you're going to implement that, and that's going to really be a core of how everything works. And then if you take more advanced classes, you'll see more advanced versions of these things. But it's challenging, I know, but it really gives you a good insight into how everything is going to be is put together. What we're going to cover, starting today, is the dimensionality reduction. This is a new class of problems. Okay, and it is the dimensional reduction and the clustering sections are going to be different from the linear regression and when we'll see classification, in that they are unsupervised. The regression and classification are going to have labels. These labels tell us what we want the functions to look like. We want them to look like the labels. These are not going to have that. Okay, so that makes the modeling a little bit more difficult to talk about. There's a lot more choices. Unsupervised, I like to say, is if kids are unsupervised, they can have a lot of fun, but they're going to get into trouble probably. And the same is often true with these unsupervised problems in machine learning and data mining, in that you don't have the guidance of the labels to tell you how you're doing. Okay, we're going to look at the structure of the data, and and this requires some other kind of insights to make sure everything is going right. Okay, the goal today, again, is just going to be basically to define the problem, because we're going to have the quiz 4, which will cover gradient descent. So I'm going to try and get to the definition of the problem of dimensional reduction, and then we'll talk about the kind of methods of so how to do this. The good thing about this is you're not going to have to implement doing dimensional reduction. Well, I mean, you'll implement it in the sense in that the version we're going to be talking about is solved by a classic problem in linear algebra called the singular value decomposition. And the real thing you need to learn is, what is a singular value decomposition, the SVD? What is it actually doing, and how to use it? That's something you're going to call a function. It's going to compute everything for you, but then you need to know how to interpret and use the output. So that's what we're going to focus on more in this course. Probably, how many have seen the SVD before? How many? Oh, okay, good. A few people. A lot of people, have not seen this before. It's not always taught in the linear algebra course. It should be, in my opinion, it should always be taught in the linear algebra course, but it's not always taught. So we'll go over it here. It's related to the eigendecomposition, if you've seen that, and we'll make that connection. And then I will tell you how, one way, not necessarily the best way, how to actually compute it. I think it's a little bit informative to go through that way, but you won't actually need to do that. Actually do the computation. You'll just call this SVD function. Yeah, and we'll wrap some stuff up. Okay, so that's the plan going forward. Okay, so I wanted to start by saying a few things about just coming back to the gradient descent on data. And I want to give kind of another simpler picture of what's going on, just to make sure this concept is clear. I want you to go back to, we talked in the first few weeks of the semester about this problem where we had these data points. Okay, and we wanted to model them as if these were drawn from a normal distribution, and we wanted to estimate the mean of the normal distribution. And we said, okay, that was minimized, the maximum likelihood estimator of that was minimized under the sum of the squared error. So we want to estimate, and that was minimized by the mean of these data points. If you remember that from a long time ago. But what we can think of this in the gradient descent framework as well. And the idea is we have data, and we want to associate with each data point a cost function, okay? And each cost function looks something like this. This will be f of the cost of the mean. The mean is the value that we're trying to estimate, is going to be the distance, or we can just use the x2 minus m squared, right? So that's this red cost function here of this one data point x2, right? And this is a quadratic cost function. This function is convex in terms of m, right? We choose this choice of m in here. This is the mean we want to estimate, and this is a cost. If we have m exactly at x2, the cost is 0. As we move further away, it gets higher, and this is convex, right? We can design this as a convex function. We can do the same thing for x1, right? And these also quadratics, and x3, okay? And then what we'd like to look at is a function which is, let me try and write this as something like the sum. This function is going to be the sum of j equals 1 up to 3 of xj minus m squared. Okay, we'll call this was f2, and this will just be f of m. Okay, this is the sum of these convex functions, so it has to be convex, right? So this green function is convex, and then what we'd like to do is to find the minimum, right? The minimum of the green function, that is our m star, our optimal estimator. Okay, and that turns out to be the mean of the data points if I drew it just right here. Okay, and so what we've done is we've taken this data, we've modeled each data point by a single convex function, and we've combined them into one convex function f, right? I can guarantee they're convex because they're sum of convex functions, and this f, I can run gradient descent on this if I wanted to. This is a one-dimensional problem, and there are other solutions, so it might be a little silly to run gradient descent, but this kind of illustrates, again, this transformation from the data to the function of the cost for each data, and if I add them together, I can maintain the convexity and then run gradient descent, and that solves for the model parameter of our defining our model, right, by optimizing the green function, right? So that's the big picture here. And the convexity, or the strong convexity, if we can get that, we can control that by how we build the function, and that ensures gradient descent will run very quickly. Okay, hopefully, yeah, great.
Can we do this on concave effect?
Oh, so you want to find, so if you take the negative of that function, then it will be kind of reflected down below here, right? Something, like, right, this could be negative of f.
Yeah.
Right, and then I want to find the maximum of this function. Sure, I can do that as well. I need to put some minus signs in the right place and everything will work. People typically try and write it in this way, where you're minimizing a function. It's just the overwhelmingly common framework. And I suggest you try and convert functions into things you minimize. It'll match with the literature and everything you're used to about it.
Would it still be counted as gradient descent, or would that
It'd be called gradient ascent. Yeah, but it's just negative signs pass through consistently. Yeah.
So the red ones are still 1 point, correct?
Correct. Each one is from a single data point.
And if it was like if it had 2 degrees like F and N, then that would be plane of solution for single point, correct?
Yeah. So if you could, if so say there was another coordinate out here, right? And well, I'm computing a mean, so it's a little bit, the mean would still be better to be closer to these functions. Even if there was another coordinate I could fit it on, I'm moving away from the data points that live in the plane here. So that's not good. It's not going to help. With the linear regression formula, you get these, each data point restricts one dimension of a potentially d-dimensional space, right? So you're kind of constraining one dimension at a time, and you kind of need to combine together at least d of these to make it strongly convex. And if those points, if you put them in a matrix and that matrix full rank, then it will be strongly convex. Yeah. So great. Okay. Any other questions? I want to make sure there aren't any questions. We have a quiz on gradient descent, and I'm happy to spend a couple minutes on questions. Yeah.
So this is just one way to determine if something is strongly convex or not?
Yeah. How do you determine if it's strongly convex? Yeah, it's sometimes, if you're just given a function and you want to say, is it strongly convex? You typically would only claim it is if you designed it to be strongly convex. Okay, like in this way, I designed this one to be convex because I know each of fj is a convex function, and so the sum of them is convex.
Okay.
It turns out this is also strongly convex because they're full rank because they're one dimensional, right? With the linear regression example, you need the representations of the data to be full rank. That's a way you can tell. Your data might not be full rank, and then it's not strongly convex. And sometimes weird things happen in the gradient descent because the data happen to be somehow have there's a null space, or there's some space where they didn't happen, or in deep learning, when they set up much more complicated functions to try and optimize, there are weird things that can kind of happen where you kind of lose a dimension of happening, and then the gradient descent kind of gets stuck. And there's been a whole bunch of heuristics designed to try and get around these things. But it's unless you get these clean problems like linear regression, it becomes a little trickier to handle this. Yeah.
So if we were just given a picture and the questions, like, is it strongly convex or not? We cannot determine that by accuracy.
So yeah, the intuitive way of thinking about strongly convex, right, is you have a function. It doesn't have to be so symmetric, but needs to be smooth. Okay, so it cannot have any kinks. Okay, so strongly convex should have no. I think kink is a okay word for this. No, so no kinks. So no, what I formally mean is, hopefully this makes it memorable, is no, the second derivative should be continuous, okay? That means this is a little bit more technical and a mouthful, but this second derivative should be so continuous, right? So remember, I drew this function before, which is like this, where the function was continuous, but the second derivative at this point is not continuous, right? The slope changes dramatically. Where here, this one, I mean, aside from the wiggling of my hand drawing it, is pretty much continuous everywhere. Okay. The second thing, right? What this basically means, that the second derivative is continuous, for every point I can fit another parabolic function, or two ones, on both sides that will touch it at that point. The drawing needs a little bit of precision work there, but on either side, that goes above and below the function. I can always sandwich it between two parabolas. Sum of squared functions work great with gradient descent, and strong convexity is a generalization of it that still works great. Okay, and so up until the last 3 or 4 lectures of class, we'll just be dealing with sum of squared loss functions, cost functions. In the classification, we want to use other cost functions other than sum of squares, and they're still going to be strongly convex. So I'll need this generalization a little bit for that. Yeah.
So it needs to be symmetrical and just
Does not need to be symmetrical, but it has to be smooth and smoothly changing.
like just it needs to
Yeah,
flow.
good. And it has to be convex, right? So something like this is not convex, even though it's smooth, has no kinks in it, but it's also convex, right? And also convex. This is not convex. Why is this not convex? Yeah, you can draw a line here, and the function passes above this. All right, so that's not convex. Okay. Okay, great. There are other abstractions, but this is kind of the main one people use to say gradient descent will work and work really well. Okay, great. Yeah, I think you guys are going to do okay on this. Well in this quiz. I hope so. That's my goal. That's my intention. You're asking the right questions. There doesn't seem to be. I don't understand that at all at this point. So that's good. So, the people who come to class all the time and watch the lectures, they tend to do well in the class. So I have confidence in you all. Okay, great. So let's talk about dimensionality reduction. Oh, oh, did I miss anything on the chat, Anna, or?
No.
Okay. Okay. Okay, dimensionality reduction. Okay, this happens when the idea is you have really high dimensional data and you're scratching your head because the dimension's too high, and you're like, I think there's some simpler, lower dimensional form that will work just as well. High dimensions can be problematic for understanding, right? So why kind of high dimensions so bad? I mean, they aren't always bad as it turns out, but there are things that cause challenges with them. One is hard to understand, right? If the data is in a really high dimensional space, how do I think about it, right? Like if I can get down to a 2-dimensional space, I can draw a picture. So that seems great. If I can, without distorting the data too much, get it into 2 dimensions, and I can kind of see what's going on. And as hopefully you found in the gradient descent stuff, I gave you the tools for plotting. And if you reuse those tools on the problem, they should have been very helpful. In 2D, you can plot stuff and kind of see what's going on, and that should help you check to make sure what you're doing is not too far off base from what it should be. So whenever you can plot something, you should try and plot it. It will help you. Okay, so it can be hard to understand these high dimensions. So if we can get it down to 2 or maybe 3 dimensions, that should be great. The other thing is that can be computationally expensive. Okay, so if I'm, yeah.
When you're working on high dimension data, there's no guarantee that's not correct.
Yeah, you know, the data points will be, in this class, we're thinking about data as just points, right? And the points itself don't know about like linearity. The models bring the linearity into it. Yeah, so yeah, so it's, okay, good. So it's computationally expensive, right? So if I read one point, the cost is going to be O of D, right? Big O notation, hopefully you're familiar with this sort of thing. If not, don't worry, but it takes D cost to read a point because it's a vector of length D. If D is 1,000,000, and there are data sets that have 1,000,000 dimensions, it takes 1,000,000, I have to read that, it takes 1,000,000 amount of time, right? I'd rather it be smaller. 100 dimensions is much less. Okay, so some things go from 1,000,000 down to 100 dimensions. We'll mostly talk about things that work well in from hundreds down to 2 or 10 dimensions in this class, but you know, that's one example. Still, I'd rather be 10 dimensions than 100 dimensions. I save a factor of 10 in the runtime every time I look at a point. So computationally, it can be expensive. There are other things we'll see in the, for instance, in the clustering section, that have something called the curse of dimensionality. Curse of dimensionality. Okay, so I guess close to Halloween, this is a good thing to talk about. The curse of dimensionality is some algorithms. These are kind of algorithms that have runtime basically often look like n to the power d. Or they could be just some structure you want to kind of work with, has complexity n to the power d. So that means they grow exponentially in dimension. So if you're in 10 dimensions, this could be infeasible to do. If you're in 2 dimensions, quadratic might not be so bad. Okay, so sometimes dimension is like a real big pain point, and we'll see something in clustering that exhibits this property. Okay, and then the other reason is sometimes you might say over fit, right? And this would be like if you're doing kind of linear regression with lots of parameters, right? If you fit a linear model with the dimension is very high, you might end up overfitting because you have you have D parameters you can learn in linear regression, and that might be way more than you have data. There are other ways of dealing with this, but one is to reduce the dimensionality of the data first, and then run standard linear regression afterwards. Right. So these are reasons you might want to reduce the dimension of your data. Okay. Hopefully that's kind of pretty natural to think. Lower dimensions seems nicer. Sometimes you want the dimensions for flexibility in modeling, but sometimes you don't want to go too far. There's kind of some sweet spot probably. And if you have too many, you want to get back down to a smaller number. Okay, so our input in this setting is going to be some data set, A1. I'm going to use A for reasons that maybe will be clear, up to AN. And each of these is going to be, and the set is going to be an element of RD. And I'm going to say that D is big. Okay, whatever it means to be big here. Typically, in this class, it's not always the case, but typically we're going to often assume typically N will still be larger than D. The examples we'll look at. This won't always be the case, but so this is, so sometimes this will be true, and we'll just think we have more data points than dimensions, but the dimension is still larger than we want. Okay, this will be easier to think about for now. Okay, and this part of the class is gonna be high-powered linear algebra. We're gonna use the power of linear algebra a lot in this section. And so what's the first thing that we want to do with this? Instead of thinking about a set of data points, we want to think about our matrix A, our data A as being a matrix. Okay, a matrix I'll draw as like this rectangle, right? It's got n rows and d columns, right? So n rows and d so columns, right? And so each row AI, this is going to be one of the data points, right? So this is one data point. Okay, so this is one data point, and I've got n data points, and they're all in this, they're stacked in this matrix. Each column is one dimension here. Okay, so this is how we're going to think about our data as a matrix, and we're going to kind of, the SVD, which we're going to call starting next lecture, is going to take the input as a matrix. And it'll be specifically, think of it, operate on it as a matrix with linear algebra tools. Okay, we'll think about this both as points and as matrices, but the SVD will only see it as a matrix. Okay. Okay, and an important part about this is that for dimensionality reduction, we need one other constraint here, which is a little bit less like mathematical and more like you need to think about the modeling of your problem. And that is that so each AI, you want to think of this as AI1, AI2 up to AID. And okay, we're going to kind of apply some black box algorithms from linear algebra, but we want to think about what these coordinates mean while we do that. If we just apply the linear algebra, things can go wrong. And one of the reasons is we want these, for this to be meaningful, we actually need that the coordinates all are kind of similar nature here. If I want things where an example would be, I have so I have n kind of so weather stations, right? So this would be, I have n data points, and each weather station has d kind of days of the so the max so of like the maximum temperature on that day, right? So I have a whole bunch of N weather stations, and each day, and there are D days, and each day I want to collect the maximum temperature. Okay, this would be an okay data set to work on. And I say, well, the D days, there's some pattern over the days. I want to find some reduced representation of these patterns. I have another example of this. Might be if I have, say, so I have N, so if what a common data set for things like Netflix and recommendation system, they have N users, and so there are D, so movies, and each pair, Aij, is I rates movie J. Okay, so it gives a rating, say, between 1 and 5. But each entry in the matrix is representing a rating of a movie. Okay? You could also have kind of, so you could have something where you have N days of stock prices. Okay, and now what I'd like to do is I would like to consider building a model where I predict the stock price on the next day. Okay, what you typically do, you have a log of these stock prices. This is big N. And I want to look at a set of D days. Okay, this could be like, 7 days. And I want to predict what this next day is going to be. Okay, so what I would do is I would take this consecutive set here as one of the data points. Okay, and then I take the next consecutive set of 7 days, and this is the next data points. Okay, and so then N is going to be N minus D. I'm going to have N consecutive sets of D days. Again, each element of here and each element of here is the stock price. Okay? Okay, what's common about all of these representations is that every entry in the matrix should have roughly the same units. It's measuring roughly the same thing. Okay, in all the dimensional reduction we'll basically talk about in this class, we will need to have them like every kind of every Aij should basically have the same units. If we don't do this, these algorithms are actually not going to make sense. I gave examples earlier with linear regression where for instance, we had this example with this website where we had the user, how much time they spent on there, how much they scrolled, how much they were doing jiggling of their mouse. And those are different quantities. Those are different columns. If I do dimensional reduction on that, the algorithms actually won't really, they don't know how to handle those different units. And this is kind of implicit in the algorithms and often is ignored. I don't want you as my students to ignore this. Okay, the algorithms don't actually make sense if you run them on that sort of data. Okay, so this is important. Okay, if you're downstream and you're using these tools on data that has a mixed match of units, you're kind of just like, you're doing some nonsense stuff. Okay, here, I want to show a picture. This is from inside my book, a different chapter. This is I really like this sign. So there's this is a city in California has this sign up, right? They have their population, feet above sea level, the data was established, and they've added all of these up. Okay, yeah. I mean it's pretty funny to see this, right? If you are doing dimensionality reduction with mixed units, this is what you're doing. Okay, you're going to do this at some internal steps someplace, and it really won't make any sense. Okay, yeah, I wanted to include this picture in my book. I found it online. I wasn't sure if I could use it, and I had a deadline to turn it in, and I almost drove out to California to take my own picture, so I didn't have a copyright issue. But I figured out I could use the picture, so that was good. Okay, So don't, don't apply this when the units mix. You're gonna, and hopefully we'll see that when we go through the mathematics over the next few lectures of what's going on. Okay. Yeah, what time do we need to stop for the quiz? 11:35? Okay, great. Okay. Okay, so how are we gonna, what is this problem of, this is the input data. Okay, we want to find lower dimensions. What does that mean? To think about that, we need to think about, so projections, okay? This means we're gonna look at linear methods. Okay, the data is not linear, but we're gonna, again, look at a linear model. And so we're gonna look at linear projections to get to the lower dimensions. Okay, so this is this is based on this dot product that we've seen before. We want to look at, we have, let's say we have a data point AI, and we have a unit vector V, right? Both of these are going to live in RD. Okay, and then the dot product is AI dot V. Remember, what is this? How can we think about this? Right, we have kind of a unit vector V. We should think about this coming from the origin. The length is 1. Right? This line, but it extends. We could think about the line that goes through here. And then we have a data point, AI. And the dot product, what is that telling us? One way of interpreting this is that it is, think of related to this projection, this dot product is giving us, if I look at the length of this projection, the length of here is VAI, if V is a unit vector. It's one way of interpreting the dot product. It's the length if I project it along V. Okay, we talked about this before. But what we want is a little bit something else. We want actually this point here. So this point, we're going to call this point the projection onto V of AI. We want that point instead. Okay, so I say this V represents a subspace that goes through that vector, a one-dimensional, so a line that goes through the origin. So it can be really high dimensions, but it's still a line. And then I want to find the closest point from AI onto that line. Okay, so this projection of AI, and this is a pi, I use a pi symbol as the projection. Okay, the projection of V onto AI. This is the closest point on the line through V to AI. Okay, they both live in D dimensions. I find the closest point. And I can write this as, there's a simple equation for this. Again, it's the dot product of V AI. Remember, that's the length. But I just say, well, to put it in RD, I multiply it by this unit vector V. This is now an element of RD again, right? VAI, the dot product, is a scalar. That's the length. And this gives a vector. And I say, how far along that vector should I go? Right? So I have the blue vector V. And how far along it should I go? I go that length, that green length, and that gets me at that orange point. Okay, so this is a projection operation onto this unit vector V. Okay, this has reduced the dimension of any, if I take all my data set, if I have multiple data points and I project them all into V, I've reduced it to one dimension, actually. This gives me a dimensional reduction down to one dimension, which is along this line through here. Okay. Good. So you've seen this before. Hopefully this is kind of, you're a little bit comfortable with this idea. What we want to do in this problem is not restrict to one dimension, but we want to allow it to go down to multiple dimensions. We want to not D, something smaller, we'll say K dimensions. Okay, so K is something, maybe K is 2 dimensions or 10 dimensions. How do we project onto K dimensions instead of 1 dimension? Okay, so for multi-dimensional projections, we need a subspace B. Okay, this will be, we want to project onto a subspace. Oh, question. Yep. Right, we're going to project onto this subspace B. And so we want to do something like this, but multi-dimensional. Okay, and so I'll call B the subspace, and I'm going to associate B with a basis. Yeah, we'll assume it contains the origin, contains the 0 point. Remember, the 0 point is right here. So we're going to assume that the subspace contains this point. We'll remove this assumption eventually in a week or so. Okay. Okay, and so we're going to represent this by a set of basis, so vectors. We'll call this VB. This will be V1, V2, up to, say, VK. It'll be a K-dimensional subspace. So this is a K. So this will be K-dimensional subspace. These all lie still in, just like before, in RD. They're still full dimensional vectors. Okay, and we're going to have, for this to be basis vectors. In fact, I want them to be orthogonal basis vectors. So, or orthogonal, that means that so first I'm going to have that each VI, the norm is 1, so they're all going to be unit vectors. And then for all VI, VJ, the dot product is going to be equal to 0 for I not equal to J. Okay, so they're going to be all orthogonal with each other, and they're and the norm is always going to be 1. So I'm going to have these two properties for my orthogonal basis. Remember, we reviewed this in the linear algebra section. So our orthogonal basis. Okay, and the cool thing is that for now I have that for any x which is in this basis, this x is an element of RD, right? I can write, then I can write x is equal to I equals 1 to k, or j equals 1 to k of some alpha j times vj. Okay, if x is in this basis, right? If I have this subspace, a basis is going to be a subspace I want to project onto. If x lies in that subspace, if it's in the subspace, then I can write it as a linear combination of these vectors. I can scale, so alpha is a scalar here. This is a scalar, and if I choose that, k alpha parameters, I can represent that point. Okay, so this is what I have of a basis. Yeah.
How is VB and RD if K is
each element, this should be slightly wrong notation here. This is a subset of RD. So each vector is an element of RD, right? I think of it as it's a d-dimensional vector. So each VJ is an RD, and I'm k vector. So think of They can be key points, but they're going to be, I'll think of them as unit vectors in this case. Make sense? Okay, great. Okay, good. So now I want to define a projection onto this basis. Okay, good. So a projection onto B, this is going to be a pi onto B instead of onto the one-dimensional line of vector A, right? This is going to be equal to, now I can write this using all of these vectors, and it's crucial that they're orthogonal. It's going to be the projection onto Vj of A, right? I'm just going to sum up the projections onto each of these VAs. Each of these projections gives me a d-dimensional point on an orthogonal space. If I add them up, it's going to give me the full thing, right? So this is equal to j equals 1 to k. The dot product onto that jth basis vector times that basis vector, right? Okay. So I'm going to draw a picture on the next page once you've written this down. Okay. So the way to think about this is, let's say I'm in 3 dimensions here. Okay, let's say I'm in R3, and I'm going to have 2 basis vectors, V1 and V2. I'm going to have a point A, with just one point A, and I want to project it onto this subspace. Okay. Right, A lives, these all live in 3 dimensions. I can't really draw 3 dimensions, but kind of pretend with 3 dimensions here. And I want to project A onto the closest point, pi of B of A. Okay, and what I do is I am going to project 2 things separately here. I'm going to project onto, this is pi of V1 of A, and this is pi of V2 of A, right? And these are both points in 3 dimensions, right? And I add them up, right? If I do vector addition on these 2 vectors I get, I'm going to get this point, right? And I'm going to think of this as, this distance is alpha 1, and this distance is alpha 2, and these are in fact coordinates in this 2-dimensional subspace, where these alpha 1 is the length, this is A V1, and this is equal to A V2, the dot products. These are going to give me the dimensions in this 2-dimensional space. I've gone from 3 down to 2 by doing 2 individual projections and just adding them up. Because they're orthogonal, they measure different things, and I can add them up and recover stuff. Okay, I'm going to draw one last picture and we'll stop. Not going to write the math down even. Okay.
Just a picture.
Just the picture. I don't think we have enough time for the math. We'll do the math on Tuesday next week. Okay, and we're going to have now a bunch of points: A1, A2, A3 up to A4, and then I want to project, there's some subspace here with V1 and V2, and for each of these, I'm going to project them in our orthogonal projection. Okay, some from above, some from below. Okay, and these are going to be my errors. The length of the projection is my error, and I'm going to minimize the sum of the squared errors over the choice of the subspace. So I'm going to find the subspace given a data set that minimizes the sum of the squared errors of this projection. This is the problem that we're going to study. Okay, so that's how you define this projection, and we're going to now choose V1 and V2. Those are going to be the parameters given the data set that minimizes this. And that's what the problem we're going to be studying this kind of next few lectures. Okay, so hopefully that makes sense. We'll kind of review this next lecture and it'll become a little bit more clear. And then we'll apply the magic of the SVD to spits out the solution for us. Okay, great. We'll stop here so you can do your quiz, and hopefully we'll see more about this in the next few lectures. And again, I recommend